Welcome to the Deep Dive, the place where we synthesize expert research and real-world data to deliver the essential knowledge you need. Today, we are diving deep into, well, probably the biggest source of anxiety surrounding electric vehicles, the battery. You hear it all the time, right? Especially if you follow the EV conversation, particularly from folks who are maybe a bit skeptical. They often voice that common, slightly chilling concern, oh, it won't last more than a couple of years. And replacing it, that'll cost a fortune. And, that fear isn't totally out of nowhere. It's kind of rooted in our everyday experience, isn't it? Like with old smartphones or laptops where the battery just gives up. So people look at that big, expensive pack under the car floor and see, maybe, a ticking time bomb. Our mission today is pretty simple. We're going to use some really advanced scientific modeling, plus vast real-world data. We're talking tens of thousands of vehicles here to try and resolve that anxiety. But crucially, we want to go beyond just saying, don't worry. We'll reveal actionable ways you can actually manage your battery's lifespan.
And, maybe even more fascinating, show you how car engineers have designed some pretty sophisticated control strategies to boost durability. Okay, let's unpack this.
Yeah, and what's fascinating right off the bat is how the high-level data really clashes with that popular anxiety. But the full picture is definitely more nuanced. Our source material today is actually quite nicely split. On one hand, we've got large-scale empirical, real-world data from organizations like Geotab. This shows exactly how degradation happens out there with everyday drivers. And then on the other side, we have these advanced scientific models. They're often called pseudo-two-dimensional or P2D models. Engineers use these to really understand the microphysics, the chemistry of aging, and then design the control systems in the car. The core tension really running through all this research is this fundamental trade-off to maximize battery life, to get that potential 2-decade lifespan we hear about engineers. And by extension, you as a driver often have to compromise a bit on vehicle performance.
Compromise how? Like slower acceleration?
Exactly. It could mean potentially limiting maximum acceleration, maybe restricting the usable driving range slightly, or even extending charge times. It's this central balancing act. So our goal for you, the listener, is to walk away understanding the key control variables, what you can manage through your driving and charging habits, and what the vehicle's sophisticated battery management system, the BMS, is actually handling behind the scenes.
Okay, let's start then with the big picture, the real-world data. Because honestly, the news here is pretty positive, much more optimistic than the skeptics might lead you to believe. We got this recent data from Geotab analyzing, over 10,000 electric vehicles in actual use. And the results, they're incredibly encouraging.
They really are.
The average annual degradation rate for EV batteries isn't just holding steady, it's actually improving quite dramatically. Just a few years back, analyses put it around 2.3% per year.
That was a 2019 figure, yeah.
Right. But the newest analysis, it reveals that rate is now down to an average of just 1.8% per year. That's significant improvement in durability in a pretty short time.
It is significant, and that reduction, it speaks volumes. It's not just about small tweaks in battery chemistry, though that's part of it. Critically, it's about the maturity and, frankly, the sophistication of the thermal management systems and the software controls that car makers are implementing now.
They're learning fast.
They are learning very quickly how to protect those cells better.
So if this improved 1.8% annual rate holds steady, and the data suggests it probably will for many vehicles, the optimistic projection gets really interesting. We're talking battery packs that could last 20 years, maybe even more.
20 years.
Think about that.
Yeah.
In places like Europe, the average lifespan of a car on the road right now is, maybe 13 years? So this means the battery is potentially set to outlast the car itself.
It's a fundamental shift in thinking. And that longevity, it translates directly into retaining usable range over time. The research projects that even after 2 full decades of ownership, the average owner can likely expect to retain somewhere around 64% of the original available mileage.
Okay, 64%. So that's definitely a loss of range. You can't ignore that.
Mm-hmm.
But it still means the vehicle remains completely usable for most daily driving, commutes and errands for its entire expected life.
Absolutely. For the vast majority of trips, it's still perfectly adequate.
And what about that nightmare scenario? The catastrophic failure, the battery just dying and needing a hugely expensive replacement.
Yeah, that fear, the multi-$1,000 paperweight idea, it's largely unfounded statistically in modern EVs. The actual failure rate, where a battery truly dies prematurely and needs a complete replacement outside of the warranty period, it's minimal. We're talking under 0.5%, really quite low.
Less than 0.5%.
Exactly. So the useful mindset shift here, I think, should be moving away from worrying, Will the battery just fail completely? And thinking more like, okay, how do I actively slow down the inevitable natural capacity loss that will happen over time?
That's a really key distinction. It's about management, not just fear of failure. Now, you mentioned capacity loss isn't just a smooth, straight line downwards over those 20 years. Can you elaborate on that, the nonlinear nature of it?
Right, it's crucial to understand the shape of the degradation curve. Capacity loss doesn't happen smoothly or linearly, even though that 1.8% average sounds low when spread over 2 decades. If you were to plot the battery's health, its state of health or SOH, over its lifetime, you'd see a distinct pattern. Typically, there's an initial, somewhat steeper drop in capacity that happens in the first few years of the battery's life.
The first year or two.
Usually, yes, maybe the first 1 to 3 years. Then, this initial drop is followed by a long, moderate period where the rate of loss actually slows down quite considerably. Degradation becomes very gradual, almost linear, but much flatter. Then, potentially, right towards the very end of the battery's usable life, and this could be after many, many years, you might see a final, more significant drop in the state of health. It's often signals it's approaching its retirement point, maybe around the 70% or 60% SOH mark, depending on the manufacturer's definition.
Okay, so let me make sure I've got this. If I buy a brand new EV today, and after maybe, say, 12 or 18 months, I notice my maximum range seems a bit lower than when it was fresh off the lot. That steeper initial dip is actually expected. It's not automatically a sign that my battery is faulty or dying fast.
Precisely. That initial settling in period, that steeper drop, is a known part of the battery's stabilization process. We can actually connect that back to the microphysics, the chemistry changes happening inside later on.
Right.
But yes, knowing this curve exists is really essential for setting accurate expectations as an owner. You don't want to panic unnecessarily.
Good to know. So what causes this degradation? You mentioned two fundamental types of aging.
That's right. The research breaks down aging into two main categories that help explain why capacity is lost over time. The first is calendar aging. This is degradation that happens simply because the battery exists, it's storing energy, and time is passing. It happens even if the vehicle is just parked for months, not being driven at all.
Like rust on a parked car, but chemical.
Kind of, yeah. Think of it as the inevitable, slow chemical side reactions occurring inside the cell over time, just associated with the battery storing energy at a certain voltage and temperature.
So even if my EV is sitting nicely in the garage, the aging clock is still ticking chemically.
That's right. And the second category is cycle aging. This is the degradation that's directly related to the charge and discharge cycles, how much you use the battery. And crucially, cycle aging is strongly dependent on how the battery is utilized. How much energy you pull out in one go, how fast you pull it out, like during hard acceleration, and how frequently you cycle it between high and low states of charge.
So calendar aging is about time and storage conditions. Cycle aging is about usage patterns.
Exactly. And regardless of which type of aging is dominant in a particular situation, the macroscopic effects what you, the driver, actually experience are the same. First, you get a loss of total storage capacity. That means your driving range decreases. Second, you see an increase in the battery's internal resistance.
Okay, what does increased resistance mean practically?
It means the battery can't deliver power as efficiently or accept charge as quickly. So you might notice slightly less punchy acceleration over time, or perhaps reduced effectiveness of regenerative braking, especially when the battery is cold or very full.
Got it. Capacity loss and power fade. Okay, let's dive into what causes this aging. What are the main stress factors?
Okay, so now we drill down. Decades of empirical studies on lithium-ion batteries have really identified three main stress factors that accelerate both calendar and cycle aging. The first one, and probably the most easily understood, is temperature. Let's call it T. Cycling a cell, or even just storing it at high temperatures, degrades it significantly faster. Period.
And the real-world data backs this up strongly.
Absolutely. The Geotab data confirms it clearly. EVs that operate primarily in hot climates, and the research often defines this as places experiencing, say, more than 5 days per year where the temperature gets over 80 degrees or about 27 degrees C. Those vehicles show a statistically significant accelerated decline in battery health compared to identical vehicles driven in temperate climates.
So just to be clear, the lifespan of my EV driven mostly in Phoenix, Arizona, is likely going to be shorter than the exact same model driven mostly in, say, Oslo, Norway.
That is a very accurate generalization based on all the available data. It's one of the most consistent findings.
Which immediately brings us back to the car's design, right?
Yeah.
Specifically, the cooling system.
Precisely. And we have a really powerful specific example right from the sources that illustrates this perfectly. Let's compare two cars from the same model year, 2015. First, the 2015 Tesla Model S. It used a robust, active, liquid cooling system coolant circulating around the battery modules. Its average annual degradation rate was measured at 2.3%.
Okay, 2.2%.
Now compare that to the 2015 Nissan Leaf from the same era. The Leaf used a simpler, passive air cooling system, basically just airflow over the battery pack. Its measured degradation rate, 4.2% per year.
Wait, 4.2% versus 2.3%. That's nearly double the rate of capacity loss,
Yeah.
just because of how the car manages heat.
Exactly. That's almost twice as fast. And that magnitude of difference really hammers home why thermal management is arguably the single most important aspect of battery longevity that the manufacturer controls through design.
So liquid cooling systems are just demonstrably better for making batteries last longer.
Yes, because they actively pull heat away from the cells, especially during stressful situations like fast charging or demanding driving, minimizing the time the cells spend at those damaging high temperatures.
Okay, temperature is critical. Factor one, what's number two?
The second major factor is the state of charge, usually abbreviated as SOC, or you can think of it in terms of the battery's voltage, as they're directly related. Lithium-ion cells, chemically speaking, are most stressed when they operate at extreme SOC levels. That means very low, near empty, or very high, near full. A lot of previous research established pretty clearly that operating below about 20% SOC and above about 80% SOC generally accelerates the chemical degradation mechanisms inside the cell.
Ah, okay. And this connects directly to that common piece of advice you always hear for EV owners, right? For the typical NMC or NCM batteries, that's nickel, manganese, cobalt chemistries, which are very common.
The most common in long-range EVs, yeah.
The best practice for daily driving is try to keep the state of charge roughly between 20% and 80%. Don't regularly drain it way down, and don't constantly charge it right up to 100% if you don't need to.
Correct. That 20 to 80 guideline is designed to minimize the voltage-induced chemical strain on the cell structure, particularly on the cathode material at high voltages and the anode at very low voltages. It's important, though, to mention the exception here. LFP batteries, that's lithium iron phosphate. If your vehicle uses LFP chemistry, which is becoming increasingly popular, especially in standard range models.
Like some Teslas and Fords now.
Exactly. LFP cells are inherently much more robust at high states of charge. They don't suffer the same level of stress near 100% as NMC cells do. So generally, LFP batteries are much happier being charged to 100% regularly. That 20-80 rule doesn't really apply in the same way.
Good clarification. Okay, so we have temperature, state of charge. What's the third big stress factor?
The third one is the C rate, which basically refers to the current being drawn from or pushed into the battery. High currents, whether they're being pulled out during really aggressive acceleration or pushed in during very fast charging, cause faster degradation.
C rate, how is that defined exactly?
It's defined simply as the operating current, measured in amps, normalized by the nominal capacity of the cell, measured in amp hours. So a 1C rate means you're drawing enough current to theoretically discharge the entire battery in 1 hour. A 2C rate would discharge it in half an hour, and so on. Higher C rates mean higher currents.
And why are high currents bad? Is it just heat again?
Heat is a major part of it, yes. High currents inherently generate more internal heat within the cell due to resistance, what's called Joule heating. But it's not just heat. High currents can also increase mechanical strain inside the delicate structures of the electrode particles and potentially accelerate some of those unwanted side reactions, like lithium plating on the anode, especially during charging at low temperatures.
Okay, and this is where our charging habits really come into sharp focus, right? The data shows the frequent use of direct current fast charging, or DCFC, those super fast chargers you find on highways.
Right, the ones delivering 50 kilowatt, 150 kilowatt, or even 350 kilowatts now.
That significantly impacts degradation rates compared to slower charging. Why is DCFC so much harder on the battery than, say, my level 2 charger at home?
Well, it's kind of a double whammy, especially if conditions aren't ideal. First, DCFC equipment uses extremely high currents. By definition, that's how it charges fast. As we just discussed, high currents generate significant internal heat. Now, if you couple that high charging current with a hot ambient day, say you're fast charging in the summer heat after driving hard, the battery temperature can spike quite significantly. And we already know high temperature is enemy number one, so you're hitting it with high current and high heat simultaneously. Yeah. Level 2 AC charging, the kind you typically do overnight at home or at work, operates at much, much lower currents. maybe 610 kilowatts compared to 350 kilowatts. So it generates far less internal heat and is inherently much gentler on the battery chemistry.
So it really is that classic trade-off,
Mm-hmm.
the convenience of speed right now versus maximizing the battery's longevity over the long haul.
Precisely. Using DCFC occasionally when needed for long trips is fine, that's what it's there for. But relying on it for daily charging, especially in hot climates, is generally advised against if you want to maximize lifespan.
Okay, that makes sense. Now, here's a finding from the Geotab study that genuinely surprised me because it seems a bit counterintuitive at first glance. The data showed that vehicles with really high usage driving lots of miles per year do not necessarily experience significantly greater battery degradation than lower used vehicles. The difference in capacity loss they found was minimal, something like only 0.25% over 4 years.
Yeah, that often surprises people.
Why isn't simply using the battery more, putting more cycles on it, accelerating its decay more noticeably?
This is a really critical distinction that helps clear up a major misconception. The mileage itself, or even just the sheer number of charge-discharge cycles in isolation, isn't the sole primary driver of accelerated aging in many real-world scenarios. The study concluded that the slight degradation acceleration they did observe in those high-use vehicles was actually attributable to something else: the need for more frequent DC fast charging to support that high mileage demand, especially if those high-use vehicles were operating in hotter climates where the fast charging is even more stressful.
Ah, so it's not the driving, it's the charging needed to enable the driving.
Exactly. If a high-use driver, maybe a taxi or a delivery van, can consistently recharge using gentle overnight level 2 AC charging, the rate of battery degradation actually approaches that of a low-use vehicle that's charged the same way. So the key takeaway here is actually quite positive for using EVs. High vehicle utilization is great. It's encouraged even to maximize the economic benefits and reduce the total cost of ownership. You just need to optimize the charging methods to avoid that daily reliance on high-stress fast chargers whenever possible.
That's a powerful clarification. So the issue isn't driving 50,000 miles a year. The potential issue is that driving 50,000 miles a year might force you to hit a fast charger 4 times a week. And that's what adds the extra stress, especially if it's hot out.
You've nailed it. That's the nuance.
Okay. One more factor from this section, buffer effects. What are these?
Right, buffer effects. This is a really important engineering factor that manufacturers use to help manage all three of those stress factors: temperature, SOC, and current behind the scenes. Buffers are essentially the manufacturer's vital internal protection system for the battery. Automakers deliberately implement charge buffers to control the usable state of charge window that you, the driver, see and interact with. They effectively mask the battery's true chemical extremes.
So when my dashboard says 100%, it's not really 100% of the battery's chemical capacity. And when it says 0%, it's not truly empty.
Correct. There's usually a hidden buffer at the top, meaning 100% displayed might be only, say, 95% of the true chemical maximum. And there's a buffer at the bottom, so 0% displayed might still leave 5% or 10% of the actual chemical capacity remaining. These buffers prevent the driver from accidentally pushing the cells into those really high stress voltage zones, the absolute chemical 0% or 100%, which we identified earlier as being particularly damaging.
Okay, so a larger buffer means the manufacturer is protecting the battery more aggressively. And it also means less usable range for the driver from the same size pack.
Exactly. It's another trade-off made by the engineers this time. Less usable range day to day, but potentially slower degradation over the long term.
Can you give an example of a car known for large buffers?
The sources often highlight the original Chevrolet Volt plug-in hybrid as a classic case study. It was well known in engineering circles for having very large top and bottom buffers on its battery pack compared to many other EVs of its time. And the result? Data showed the Volt's battery exhibited slower than average degradation over its lifespan. It clearly demonstrated the long-term benefit of sacrificing a bit of usable range up front for that maximum protection, especially from those high SOC levels.
Interesting. And this leads to a practical, actionable tip for drivers, right? We can sort of replicate this buffer effect ourselves.
Yes, absolutely. Most modern EVs allow you, the owner, to set a custom charge limit through the infotainment system or a smartphone app. You can choose to charge to, say, 75% or 85% for your daily needs, instead of letting it go all the way to the displayed 100% every single time.
So by setting that lower limit for daily charging?
You are proactively keeping the battery out of that higher stress, high voltage range near the top, even beyond the manufacturer's built-in buffer. This can further extend the battery's chemical life over many years.
And you just reserve that full 100% charge, whatever the car allows, only for those specific long road trips where you genuinely need every single mile or kilometer of range.
Precisely. Charge it fully right before you depart for the long trip, but for daily use, stopping at 80% or 85% is often a great strategy for longevity, especially with NMC and CM chemistries.
Okay, that covers the big factors we see in the real world: temperature, SOC management, charging speed, and buffers. Now, let's zoom in. Let's go microscopic. To really understand why these factors matter, engineers use these incredibly detailed scientific models, like the PDD models you mentioned, often combined with post-mortem analysis, basically, taking apart old batteries to see what failed.
Exactly. These advanced physical models are essentially sophisticated computer simulations of everything happening inside the battery at a very fine level. They model how the lithium ions move back and forth, how the electrode particles might crack or change structure, how unwanted chemical layers form on surfaces. They allow researchers and engineers to pinpoint precisely which parts of the battery are degrading under different conditions, and crucially, why we see that nonlinear degradation curve we talked about earlier, that initial steeper drop followed by slower aging.
Okay, it sounds incredibly complex. Let's try to simplify it. What are the main sort of chemical bad guys? The primary degradation phenomena identified by these models.
The research generally points to three key degradation phenomena. The first, and often considered the most dominant degradation mechanism, especially for calendar aging, that time-based aging when the car is parked, is something called solid electrolyte interface growth, or SEI growth.
SEI growth. Okay, for the listener who isn't a battery chemist, what exactly is the SEI layer? Can we use an analogy?
Yeah, let's try. Think of the SEI layer like, maybe like a very thin layer of plaque or even scar tissue that gradually forms on the surface of one of the battery's key internal components, the negative electrode or the anode, usually made of graphite.
Okay, plaque or scar tissue, how does it form?
It forms because the liquid electrolyte, the substance that carries the lithium ions back and forth between the electrodes, isn't perfectly stable. Over time, especially at higher temperatures and higher states of charge voltages, the electrolyte slowly decomposes where it touches the anode surface. This decomposition process creates this thin, solid, but generally electronically insulating layer, the SEI. Post-mortem analyses, where they cut open aged cells, have confirmed this. Using techniques like SIMS, they can see this layer gets thicker and covers the anode surface more uniformly as the battery ages. They even see excess oxygen trapped in it, confirming it comes from electrolyte breakdown.
Okay, so this layer forms and grows over time. Why is that bad? What are the consequences?
It has two major negative consequences. First, and most importantly for capacity loss, its formation leads directly to loss of lithium inventory, or LLI.
Loss of lithium inventory, LLI.
Right, because lithium ions from the electrolyte and the electrode are actually consumed and permanently trapped in the process of forming that stable SEI layer. They become part of the layer itself and are no longer available to shuttle back and forth to store energy. This directly reduces the total amount of cyclable lithium in the battery, which is the primary cause of capacity fade. You're losing your active ingredient.
Got it. Less usable lithium means less range. What's the second consequence?
The second consequence is that the SEI layer itself, being solid and often electronically resistive, acts as a barrier. It slightly impedes the movement of lithium ions trying to get into and out of the anode. This increases the battery's internal resistance and decreases the conductivity of the electrolyte near the electrode surface.
And increased resistance affects power output.
Exactly. It directly impacts the battery's ability to deliver high power quickly, which can limit peak acceleration, especially as the layer thickens over many years, or if it grows particularly fast due to high temperatures.
So SEI growth is kind of a double whammy. It steals your lithium, reducing range, and it slows down ion movement, reducing power. Makes sense why it's considered dominant. What's the second key mechanism?
The second mechanism is really just LLI, loss of lithium inventory, considered more broadly. While SEI growth is a major cause of LLI, LLI itself is the overarching phenomenon. It accounts for all capacity loss associated with lithium becoming unavailable for cycling. This could be due to SEI formation, as we discussed, but also potentially due to other side reactions happening elsewhere in the cell, or lithium getting trapped within the electrode structures, or plating onto the anode surface under certain conditions, like fast charging in the cold. LLI is essentially the primary metric for how much capacity the battery has lost. Think of LLI as losing the fuel itself.
Okay, LLI is the outcome lost lithium.
Right.
And the third mechanism?
The third critical mechanism is loss of active material, or LAM. Now, if LLI is about losing the fuel, lithium, LAM is about the physical degradation or chemical dissolution of the containers or structures that fuel the active materials in the electrodes themselves.
So the electrodes themselves are breaking down.
Essentially, yes. Or becoming less effective. And interestingly, LAM behaves differently depending on whether it's happening on the negative electrode, anode, or the positive electrode, cathode. Let's start with textile AM dollar, that's loss of active material on the negative electrode. The PTD modeling and postmortem analyses often show this has a characteristic pattern, a relatively steep initial growth phase, happening early in the battery's life, which is then often followed by a plateau, where the rate of textile slows down significantly.
A steep initial phase.
Mm.
Hang on, that sounds familiar. Is that connected to the initial steeper capacity drop we see in the real-world data?
Bingo, that's the current interpretation. This initial textile is thought to be related to mechanical stress and microcracking of the anode particles, like graphite, as they expand and contract during the very first charge-discharge cycles. There might also be some initial restructuring or passivation happening as part of that settling in or stabilization process we mentioned earlier. The anode takes its biggest structural hit early on and then kind of stabilizes.
Fascinating. So that initial drop isn't just SEI forming, it's also the anode structure itself adjusting, maybe even slightly damaging itself initially.
That seems to be a key part of it, yes. The battery isn't just chemically settling in, it's also physically adjusting.
Okay, and what about the other side? LAM on the positive electrode.
Right, textile loss of active material on the positive electrode, the cathode. This tends to behave differently. The models and data suggest textile often grows more linearly over time rather than having that steep initial phase.
A steady, continuous degradation.
Yes, a steadier process. And textile is known to be strongly promoted by high temperatures. The mechanisms here can include things like the slow dissolution of transition metals, like nickel or cobalt, from the cathode structure into the electrolyte, or perhaps structural changes like compagication mixing within the cathode crystal lattice. High heat definitely accelerates these positive electrode degradation pathways.
Okay, so summarizing the microphysics. SEI growth is key for calendar aging and causes LLI. LLI is the overall loss of lithium. LAM is the physical breakdown, with the negative side, Ln having a big hit early, and the positive side, LAMP degrading more steadily, especially when hot.
That's a great summary. You've got the main players.
Now let's connect this microscopic understanding back to the big environmental factors we discussed earlier, temperature and state of charge, based on what the PDD model showed when simulating storage conditions. How does temperature affect these specific mechanisms?
The models provide really clear confirmation here. Higher temperature acts as a systemic aggressor, accelerating pretty much all the bad stuff. Simulating storage at, say, 60 degrees C versus a lower 45 degrees C showed significantly accelerated LLI, meaning faster SEI growth and lithium consumption. It also accelerated that linear textile growth, more positive electrode breakdown. And, as expected, it led to faster formation of that SEI layer, resulting in a quicker decrease in the electrolyte's conductivity near the anode.
So high heat just makes everything worse, faster. It attacks the battery on basically every chemical front.
Exactly. It completely validates why effective thermal management, like liquid cooling, is so incredibly crucial for battery longevity in the real world. It's directly fighting these underlying degradation mechanisms.
Okay, temperature is bad. What did the models reveal about state of charge, SOC, during storage that might challenge some common assumptions?
Well, the models definitely confirm that the extremes are detrimental, just as the empirical data suggests. Storing a battery at a displayed 100% SOC, which corresponds to a high cell voltage, leads to more severe self-discharge and significantly accelerated degradation, particularly that SEI growth leading to LLI. High voltage stresses the electrolyte and cathode. Conversely, storing it at a very low SOC, like 10%, low voltage, resulted in very little degradation in the simulations. Chemically, it's very stable state, although obviously not practical for daily use as you have no range.
Right, so avoid 100% for storage, 10% is safe but useless. What about the middle ground, that 20-80% rule?
This is where the modeling provided a really interesting nuance, maybe even a slightly counterintuitive finding compared to the simple rule of thumb. The P2D model analysis found no significant difference in the key degradation indicators, specifically looking at TEX LAMPEA, positive electron degradation, and the decrease in electrolyte conductivity factor related to SCI impact between storing a battery at 50% SOC versus storing it at 80% SOC, provided the temperature was kept constant.
Wait a second, let me process that. No significant difference in degradation between 50% and 80% storage, according to the model.
At least for those specific degradation modes under constant temperature storage conditions, yes. The difference was negligible in their simulations.
But we're constantly told, almost religiously, to stick to that 20% to 80% rule for daily charging. If the model shows the actual chemical strain difference between, say, 50% and 80% storage is minimal, why is that 80% limit pushed so hard? Is it just about avoiding 100%?
That's an excellent question, and it really gets to the heart of translating complex engineering strategy into simple consumer advice. The model confirms the relationship isn't linear. The real accelerated damage, especially from a voltage stress perspective, occurs at the absolute extremes, getting close to that true chemical 100% high voltage and dropping below maybe 10-20% very low voltage. The chemical stress difference between sitting at 50% SOC and sitting at 80% SOC is relatively small in comparison, particularly for calendar aging mechanisms when temperature is controlled.
So why the 80% rule then?
The 80% rule is often maintained and communicated as a simple, easy-to-remember, and conservative target. Its main benefit is that it reliably keeps the average driver safely away from that much more critical 90-100% zone, where SEI growth really starts to ramp up significantly due to the higher voltage, especially during prolonged storage or calendar aging. Think of it more as a practical guideline for risk management rather than a hard chemical cliff edge at exactly 80.0%. It builds in a safety margin.
That makes a lot more sense. So the 80% limit feels less like a strict chemical law you must obey and more like a sensible guardrail to prevent you from getting too close to the real danger zone near 100%.
Exactly. It also highlights that from a pure chemical degradation standpoint, if you only need, say, 50% charge for your daily commute, charging up to 70% instead of rigidly stopping at 80% probably gains you very little extra battery life protection. But stopping earlier does save you charging time and energy consumption.
Right. The real protective effort needs to be focused on avoiding high temperatures and consistently parking the car overnight at 100%, rather than obsessing over 75% versus 80%.
That's a very practical way to look at it based on these deeper models. Focus on the big hitters, heat, and the true top end of the charge.
Okay, this understanding of the mechanisms and the trade-offs leads us perfectly into the final section. How engineers try to manage all this in the car itself.
Yes. These insights feed directly into the engineering challenge, which is essentially a closed-loop control problem managed by the battery management system, the BMS. You can think of the BMS as the tireless traffic cop living inside your battery pack. Engineers using the BMS are constantly trying to solve a tricky multi-objective optimization problem. They have competing goals. They want to minimize battery aging, let's call that cost function, J-life dollars. But at the same time, they need to maximize everything the driver actually wants and expects from the car.
Performance?
Exactly. Maximize speed and acceleration, maximize the available driving range, and minimize the time it takes to charge.
And as we've established throughout this conversation, those goals are fundamentally in conflict, aren't they?
Yeah.
If you push for maximum performance, you inevitably use higher currents, maybe push the state of charge to its limits.
And that stresses the battery, accelerating the aging process. You can't have it all the time.
So how does the BMS actually try to balance this trade-off in real time while you're driving or charging? What levers does it pull?
The BMS primarily uses two main control variables, two main knobs it can turn to manage this dynamic balancing act. First, it can actively set the maximum current that's allowed to be drawn from the battery at any given moment, particularly during acceleration. And second, it can actively limit the depth of discharge, DOD, by managing the charging process and the usable SOC window, essentially enforcing those buffers we talked about and potentially adjusting them.
Okay, IMAX and DOD limits. Let's look at the simulations discussed in the research, specifically for fully electric vehicles, FEVs. They modeled driving an FEV over a simulated 30,000-kilometer cycle under different control strategies.
What happened?
Well, first they tested the effect of limiting an IMAX, the maximum current. For example, they put a constraint on the system saying, never draw more than 0.75 C. What did that do?
They found that limiting the current did provide a small benefit for battery life. It limited the overall capacity loss, saving about 0.25% of capacity over that 30,000-kilometer simulation compared to letting the current run free. A measurable but small improvement.
Okay, 1/4% saved, but what was the cost?
The cost was an immediate and noticeable degradation of the driving experience. Limiting IMAX directly translates to limiting maximum acceleration. The car feels more sluggish when you floor the pedal. It also inherently slows down the fast charging process, as you can't push current in as quickly either.
Right, less fun to drive, takes longer to charge.
And interestingly, the simulation also showed that if the driving cycle itself was naturally very smooth, maybe just gentle highway cruising where high currents are rarely demanded anyway, then the benefit of actively limiting IMEC became almost negligible. You sacrifice driving dynamics for a tiny battery life gain, and only if you drive aggressively in the first place.
Okay, so limiting current has a small benefit but a definite performance downside. What about the other lever, limiting the depth of discharge?
Right, limiting DoD. This means actively reducing the maximum usable capacity window. For instance, only allowing the battery to be used down to, say, 50% of its total pack capacity between charges. In the FEV simulations, this strategy showed a much more powerful effect on preserving battery life. Limiting the DoD in this way saved approximately 1% of capacity over that same 30,000 kilometer simulation horizon.
1% saved by limiting the usable charge window compared to only 0.25% saved by limiting the peak current. That's 4 times the impact.
It is significantly more effective in these simulations. And this highlights a really crucial engineering point, especially when comparing fully electric vehicles, FEVs, to older hybrid vehicles, HEVs. FEVs, particularly modern ones, typically have very large battery packs relative to the power demands of the motor, much larger than the small packs in hybrids. Because the overall pack is so large, the individual cells within that pack actually experience relatively smaller C rates currents, even during quite high acceleration events.
The load is spread across more cells.
Exactly. Therefore, in these large pack FEVs, actively limiting the DoD, managing that charge window carefully, keeping it away from the extremes, tends to have a significantly more evident and powerful effect on slowing down battery aging than trying to clamp down hard on the maximum current draw, which might already be relatively modest at the cell level.
That makes sense. So for the owner of a typical modern EV with a decent-sized battery pack, outside of managing temperature, controlling your daily charging window, like that 80% limit we discussed, is probably the single biggest lever you have direct influence over for longevity.
Based on this research, absolutely. Temperature and SOC window management seem to be the dominant factors accessible to the driver for FEVs.
Okay, now we get to what sounds like the most sophisticated part, the optimal control strategy that the researchers derived. They weren't just testing fixed limits. They tried to find the absolute best way to manage the battery over its whole life.
That's right. They didn't just look for a single set it and forget it limit for IMAX or DoD. Instead, they created a theoretical optimal benchmark. They did this by mathematically weighting the performance indices, speed, range, charge time, against the battery life over a very long simulated horizon, 200,000 kilometers.
So, trying to find the perfect balance over the long haul, what did this optimal strategy look like? Was it just tighter limits all the time?
No, and this is the really key result. The optimal strategy turned out not to be a constant set of limits. It was a dynamic, time-varying control sequence. The required level of protection changes over the vehicle's life. And here is the crucial insight. The optimal strategy dictates that battery protection needs to be heavily front-loaded.
Front-loaded, meaning you protect it more when it's new.
Precisely. The optimal control requires the BMS to exert a greater control effort, be more restrictive in the first part of the vehicle's life. Specifically, the simulation suggested the first 50,000 kilometers, around 30,000 miles, are the most critical.
Okay, what does that greater control effort look like during those first 50,000 kilometers?
During this initial sensitive period, the optimal strategy derived in the paper aggressively limits the usable depth of discharge, DoD, often keeping it below 50% of the pack's capacity. And it also limits the maximum allowed current quite strictly, keeping it below a moderate 2.0 C.
Wow, DOD below 50% and IMAX below 2C. That sounds quite restrictive compared to normal driving. Why is such aggressive protection needed right at the beginning?
The rationale ties directly back to the microphysics we spent time on in Section 3. Remember how we discussed that the agent degradation rate is significantly higher during the first thousands of ampere hours processed by the battery?
Yeah, due to that initial steep SEI formation and the Lamb stabilization, the anode cracking.
Exactly, because those initial irreversible degradation processes are happening most rapidly right at the start. The optimal control strategy recognizes this. By protecting the battery really hard and early during that highly sensitive initial stabilization period, you prevent the excessive irreversible consumption of lithium, LLI, and minimize that initial structural damage, AMM. The benefits of this early protection then accumulate and pay dividends over the entire remaining life of the vehicle. You're preserving more capacity and health from the outset.
Okay, that's a powerful concept. Protecting the car when it's brand new is far more valuable in terms of long-term capacity than applying the same level of protection when it's, say, 5 years old and already stabilized.
That's the core finding of the optimal control analysis.
And what happens after that initial aggressive period, after the first 50,000 kilometers in this simulation? Does the BMS just keep those tight limits forever?
No, the control effort actually relaxes quite significantly. After that initial 50,000 kilometer mark, the underlying degradation curve has typically flattened out. The battery is stabilized. So the optimal control sequence then allows the DoD limit to relax, settling back somewhere around 50% to 60% for the remainder of the vehicle's life. And the maximum current limit also relaxes, allowing peaks up to around 2.5 C. The simulation confirmed that this dynamic strategy, tight control, early, relaxed control, later performed demonstrably better in preserving capacity over the entire 200,000 kilometer horizon, compared to just applying fixed, moderately relaxed constraints over the whole life.
So it's not just about setting limits, it's about setting the right limits at the right time.
Exactly. It's a crucial finding for engineers designing these BMS strategies. You potentially save the most long-term capacity by front-loading the protective effort.
This has been an incredibly detailed journey. We've gone from the macro-level data of tens of thousands of cars, right down to the microphysics of particle cracking and SEI layers, and back up to sophisticated engineering control strategies. I think the key takeaway for you, the listener, is really clear now. Your EV battery's life isn't just some lottery. It's not just luck of the draw. It's a direct function of informed choices you make, especially regarding temperature exposure and charging habits, combined with the highly advanced, often invisible control strategy running inside the car's BMS. And maybe the shortcut to being well-informed, the core principles to internalize, are these three. First, prioritize vehicles with good thermal management, ideally liquid cooling, especially if you're in a hot climate. Second, be mindful of charging limit routine reliance on DC fast charging to avoid unnecessary heat and current stress. Use gentler level 2 charging when possible. And third, realize that the early life of the battery, maybe those first 50,000 kilometers or 30,000 miles, is the most sensitive period, where careful SOC management potentially yields the biggest long-term benefits.
Absolutely. And building directly on that last point, that finding about the dynamic optimal control strategy, the fact that the degradation rate is highest in the first few years, and the optimal way to maximize lifespan involves potentially limiting performance quite aggressively early on. Well, this raises a really important and quite provocative question that car manufacturers are undoubtedly grappling with right now.
Which is?
Does the consumer need a new kind of interface? A new choice? Since optimal protection, especially early on, requires limiting performance like acceleration and usable range, lower DoD limits, should you, the driver, actually be given the ability to choose your personal trade-off?
You mean let the driver decide?
Yeah. Should you be able to say, you know what, for the first 50,000 kilometers, I prioritize maximum performance and accessing the full advertised range. I accept the consequence that this might accelerate the battery's aging. Or conversely, should you be able to choose, no, I want to optimize for maximum possible lifespan right from day one. I'm willing to accept slightly reduced acceleration and maybe a software-limited daily range for the first couple of years to achieve that.
Performance versus persistence, chosen by the customer.
Exactly. That choice, that fundamental conflict between getting the most out of the car now versus making it last as long as possible, is the core engineering trade-off. And the question is becoming, how much of that trade-off decision should be passed along from the engineers to you, the customer?
That is a fascinating and definitely provocative thought to ponder next time you look at that stated charge meter, a potential future direction for EV interfaces. Well, thank you for joining us today for this really deep dive into the science and management of EV batteries. We hope you found it useful. If you appreciate having these complex topics broken down into actionable, clear knowledge, please do consider following the channel for more explorations like this one. We look forward to diving into another topic with you again soon.